Welcome back to the channel. Today I'm going to show you how to get started doing some basic data sorting and filtering in medical research data sets. So the first thing you want to do is get data. So we're going to use iSpy2 as an example today. So on your browser, just search iSpy2 and you will see there's a cancer imaging archive website that'll show up. So this is actually a data set from some randomized control trials of chemotherapy agents for breast cancer, and the investigators made the data publicly available so we can use it as an example. So this data set is kind of like an Excel sheet. It's got a number of variables, so each row is a unique person and each person has a patient ID attached to them. You can tell what sort of treatment they underwent. You have HR, which is hormone receptor. So if this variable is 1, the cancer was hormone receptor positive. And HER2 is another protein. So if it's 1, that means the cancer was HER2 positive. PCR means pathologic complete response. This is if the tumor responded to treatment. So if the tumor fully shrank after chemotherapy, this is going to be a 1. And if it didn't fully shrink after chemotherapy, this is a 0. You also have age in years, race, whether they were menopausal or postmenopausal or not, and then we also had if they're Hispanic or not. Okay. So our goal is to actually, what we're going to do today is see if we can see what variables are associated with PCR. Okay, so if you download the data set, the easiest way to get started is go on Google Colab, so collab.research.google.com. Okay. And you can make a new notebook. I've already made a notebook here, so I'll just use this. Okay. So I have some code here, 2 cells that you want to run. One is basically importing a few libraries and then defining some functions. Okay. So I have the text for this in the description, so go ahead and do that. But when you enter in, you want to go ahead and upload the data set. So upload the data set. You can see I'd already uploaded it before, but you can go ahead and do that. And then run the first 2 cells, and you should be ready to go. So you can add another cell to write some code. Okay. Now, if you're not familiar with Python at all, it's going to be somewhat of a learning curve. Okay, but the simplest way to get started is using pandas. So pandas, I've abbreviated it as PD. So there's a function in pandas where you can read an Excel file in and have access to the data within Python. So the way you do that is pd.readExcel and then parentheses. And inside the parentheses, you want to put the path to the actual file. So copy path, and then you paste it in, and boom. You see we had that same Excel sheet. It's not showing every row because there's, 985 rows, so it's kind of skipping a lot of them. But you can see all the columns, right? You can see all the variables we have for every patient in the data set. Now, an easy way to do this is to set this thing, basically this data frame, we call it, equal to a thing called patients. So every time you put patients at the end of a cell and run it, you'll be able to see all the data. Okay. Now, our goal is to be able to see what variables are associated with PCR. Okay. The first thing you want to check is if how your data looks. So one of the best ways to do that is say the name of the data frame. So our name of the data frame is patients. Then within brackets, you can put the name of the column. So PCR like that. Okay. So the PCR column of the patient data frame. And if you run that, you'll see all the values. Now, it would be kind of crazy. You could do this if you want to check. If you want to check it, what's in there, you can do this. You can look at all the values, right? It's a lot to sort through. So an easier shortcut to having to look through all these zeros and ones is this function that I will show you, or this feature, where you put the name of the column and you say dot value counts, and this parentheses at the end, and you run that, and you can see within the PCR column, 668 people did not experience a complete response, 317 did experience a complete response. So that sort of gives you a summary of what's inside the column. Okay, and you can do this for all the other columns also. So you can do this for HR. So you can be like, okay, within the HR column, there's two possible values, 0 or 1, right? And same with, let's say, HER2. There are two possible values in there, okay? So our goal is to predict PCR, and it's good that it's binary and that there's only zeros and ones, okay? So the way to do this is I have created a function called logistic regression. And the way it works is that you can basically get an odds ratio out of it, and I'll explain what that means. So first item, you put the name of the data frame that you have your data in, okay? Then you want to put the column that you want it to be the outcome. Okay, so the outcome is PCR, whether their tumor shrank or didn't shrink fully after chemotherapy, so PCR. Then you want to put predictors. You usually want to put a list of predictors. So predictors are things that we want to see if they're associated with PCR. So you can put, let's say, hormone receptor and see if having hormone receptor positive breast cancer is associated with, experience a complete response. And you run the regression, and you see that basically having hormone receptor positive breast cancer has an odds ratio of 0.37. Now, what does that mean? What that means is that if your breast cancer is hormone receptor positive, your odds of experiencing PCR are 0.37 compared to if you're hormone receptor negative. So if this number was 1, if this odds ratio was 1, that would mean that PCR has nothing to do with hormone receptor positive breast cancer. But if it's less than 1, that means people who are hormone receptor positive are less likely to hit PCR. And if the number is bigger than 1, let's do an example where it would be bigger than 1, HER2, which is another protein that might be overexpressed. If you actually have HER2 receptors on the tumor overexpressed, you have a 2.7-fold higher chance of experiencing PCR, okay? And this p-value just tells you that, assuming there's no fundamental difference between these groups, this is the probability that you get a result this extreme. So that's what the p-value means. Okay, so let's try and predict PCR using more variables. We've used hormone receptor and HER2, but there's a lot of other information available. There's age at screening, so we can use that and see if age is associated with, with getting PCR. Okay, it errored. So it says exop contains, okay. So usually we didn't check this variable. You can do the same thing I just did before, which is patient's age at screening dot value counts. The problem with doing this is that it's a continuous variable. So, there's all these ages you could be, all right? If you have a continuous variable like this, it's easier to use describe. What you'll notice is the mean age is 48.7, the median is 49, the oldest person is 77, the youngest person is 41. The youngest person is 23, sorry. Okay, what's the problem here? If you look at count, which is the number of people who have an age, it's actually 982. But if you notice, we have 985 rows or 985 unique patients. That means probably 3 people don't have an age inputted in. So the way you would actually check for that officially is you can say is null and then dot sum. And that will give you the number of people who have like empty values in this column. And there's 3 people have empty values. So when you run this sort of regression, you can't have missing values. So we're going to have to exclude those people who don't have an age input. The way we do that is let's just output this and show you what this would give back, okay? If I say patients, let's say the age column of patients data frame dot is null, that would basically go in and check every cell and tell you whether or not it is empty. So most people, their age column is not empty, right? So it's therefore false. So this is saying that person 0, their age column is not empty. Person 1, their age column is not empty. It's false. If you were to set this condition equal to false, you would get the inverse. So in other words, true. Everyone's everyone is not, most people are not false, right? Most people have a value. So this is the condition. We want to only keep the ones that are true, meaning the ones that have an age input. So what you do is take this condition and put it inside of brackets, and then put the name of the data frame on the left, and you will get all of the rows that meet this condition of not having a empty value within the ages screening column. So you can see that we actually have 982 rows now, right? As opposed to 985 before. So you can set that equal to the patients again and put it on top. So now we only keep the rows where age is not missing, right? So we have to exclude 3 people with missing age. So now if I run it, now it works, okay? And the p-value is not very low, so probably there is no association with age. However, what this would mean, you would maybe wonder what a odds ratio means if it's like a continuous variable. All of this means is that for every year of age, there's a 1% lower chance of experiencing PCR, because essentially 1 is the baseline, so 0.99 means that there's a 1% lower chance of having PCR. Okay, so on top of age, let's try and incorporate race. Let's see if race predicts PCR at all. And we can do that by doing this. And you'll notice it won't work. Why wouldn't it work? Because all the other variables like hormone receptor, HER2, they were binary variables. There were zeros and ones, but this is categorical. There are actually multiple options. There's more than 2 races that you could be. So once again, the way we check for that is patients, race.value counts. This is a very useful feature. Okay, so within the race column, about 780 people, most people are white. Some are black or African American, some are Asian, and then you can see about less than 20 are like other things. Now, what I'm going to do, it's a little hard to, when you do modeling like this, it's hard to have categories that have such small sample size. So I'm going to basically dump all of these into an other race bucket, okay? So we'll have 4 races at the end. We'll have white, black, Asian, and other. All right. So how do we do this? Okay, so the way we do this is you can do a thing called redefining the column. So we can try and redefine the column. So we can say the race column equals, and here's the way that you dump these other inputs into an other sort of category. You put dot apply and then lambda x, and you say other, okay? If x is not in, so if the value within this column isn't white, black, or Asian, put it into the other category. So if it's not in white, black, or African American, or Asian, put it in the other category. Else, meaning if it is inside white, black, or Asian, you can keep it the same. You can keep it as X. So that's the way the logic works. And let's run that and check it again. So, yep. So you can see now how we've collapsed the other ones to this other category. Now if I run it, it still doesn't work because the column is still categorical. It's not binary. So how do we deal with a variable that has more than 2 possible options? The way we do that is we have to dummy the variable. What that means is what I will just explain. So I've created a function that says create dummies. So if you do that, you'll see, let's use it. Okay, so create dummies. You first put the name of the data frame, so ours is patients. The columns that you want to dummy, so the only column you want to dummy is race, right? So we want to dummy race column, and then you run it, and you'll see this function returns a data frame that has extra columns. So for every one of these race categories, it creates a column. So it creates a column called white, and then if the person was actually white, it'll put a 1. Right? If they weren't white, it'll put a 0. And instead there's another column for black, and that one will be ones and zeros. And there's a column for Asian that'll be ones and zeros, and other that'll be ones and zeros. So this is called dummying a variable, and when you dummy a variable, these four sort of options are mutually exclusive. So each person is at least one race, but no more than one race, meaning you can't be Asian and black at the same time, because there's only there's only black or Asian within this column, right? Okay, now that you've got that sorted, we can put age into this logistic regression model. The way of doing this, you typically want to pick one race that is the baseline comparison. So we can say, for instance, we want to compare the outcomes of Asian versus white, black versus white, and other versus white. In that case, we're setting white as the baseline. Okay. The way you do that is set white as baseline is you can delete the race one, okay? Put all of the ones that are not white into there. So Asian, you put it in the model, okay? African American, you put in the model, and then also other race, you put in the model. And you run that, and you see that it don't work because we didn't redefine it. So patience has to equal, patience has to equal this. So, okay. So now I'm gonna run it, and it works, okay. The p-values are pretty high, so probably race doesn't seem to be predictive of PCR, but what this means is that Asians have like an 18% lower chance of having PCR. Blacks have an 18% lower chance of having PCR compared to whites. So these are all relative to whites. The reason is because we didn't include white in the model. If you include white, you'll notice that it doesn't run quite well because, these categories are all mutually exclusive. So you have to exclude one category. Now, it doesn't have to be white always. You can exclude black and have that be the baseline comparison. So all these odds ratios are not comparing it to black, right? So we said how the odds ratio of white versus black was, 0.82. If you inverse that, you would get, if you inverse that for white versus black, you'll get the other way around, 1.22, okay? So that is how you run that. Now, maybe you want to include more variables in here. We can include, we can include ethnicity. Now, ethnicity, again, has text inside of it. It's not binary. We can check ethnicity and see what's in there, actually. Dot value counts. We can do it down there. Let's do that. Okay. Okay. So there's two things. Either you're Hispanic or you're not Hispanic. And the way that you would dummy that is the same thing. So you just add Hispanic to the list of things you want to dummy. And what you will notice is that it will create a new data frame where there's also a Hispanic or Latino column. There's a not Hispanic or Latino column. But of course, you only need to include this one in the model. Okay. So like that. And what you can see is that people who are Hispanic have a slightly higher chance of getting PCR, but that could easily be a false positive. Okay. So other variables, let's include menopausal status, and we'll call it a day. Okay. So menopausal status, if you check what's inside that column, it looks very heterogeneous. There are a lot of options, it seems. So if you check it, there are in fact a lot of options. So let's see, there's premenopausal, there's postmenopausal, there's premenopausal again, there is, it's not applicable, there's perimenopausal. So it's very heterogeneous, of course, but I'll simplify. So we will say we can dichotomize it as either postmenopausal or all the other ones non-postmenopausal or pre/perimenopausal. So if you're trying to dichotomize it like that, one easy way is to create a new column. So you can say patients, I'm going to create a new column called postmenopausal. And I can say that I want this column to be based off of what's already existing on menopausal status. Okay. Now I'm going to say I only want this column to be a 1 when menopausal status equals this text, okay? So I'm going to say when this equals this text, this is going to be 1. If I run it right now, you'll see that it'll create this new column called postmenopausal, and it has true and false, which is fine, but you know, we want 1s and 0s where 1s equal true and 0s equal 1. So you can surround this whole thing in parentheses and then do dot as type integer, okay? So what you'll notice is that you'll get 0s and 1s. So every time somebody's menopausal status is postmenopausal, it'll put a 1 there. And every time it's something else, it'll put a 0. Okay. So we've dichotomized that, and we can use this column or this variable as an input into the model now. So we can use that in the model as well. So boom. People who are postmenopausal have about 30% increased chance of PCR. So it really seems from this analysis we did that age, race, we can put Black or African American again just so the baseline is white patients. So age, race, and ethnicity and menopausal status don't really predict PCR very well, but the things that happen to are molecular subtype, right? Whether the cancer overexpressed hormone receptor or HER2. Okay, so I hope that was helpful. I hope that made sense. If you want to practice more, of course, I have this code in the description. You can download it, and you know, Google Colab is the easiest way to get started because this is not very computationally heavy, and they have computational resources for you to like run it, right? You can connect to Python easily. You don't have to download Python yourself. You can import anything you want, and you can mess with it. So Pandas, again, is what makes this possible. It's kind of like Excel, except a lot faster and more flexible. Okay. Last thing I will say, of course, I haven't posted in 6-7 months. I have been getting pretty tired of doing basic science sort of videos like organic chemistry, biochem, physics. I finished basically my pre-med years. I'm starting medical school soon. So I think I want to focus on newer things in this channel that I haven't explored before. And certainly one of them is data science like this. And I think that as much as I enjoyed the OrgoChem, it's kind of time to move on at this point. But I deeply enjoyed it, to be honest. Okay. So let me know if this was helpful, and see you in the next video.